Let's start with the infrared, because it gives us limited but very easy to extract information. So there are two useful peaks here. The first is this one, big broad peak at the left hand side. If you look at the wave number range for that one, you can see it's going up to about 3,600 there, and it's starting around 3,200 there, and that is consistent with not just any old OH but specifically an alcohol OH. So we know that one of those two oxygens in the structure is an alcohol OH. Make sure you didn't think that was a carboxylic acid. Carboxylic acid ones look very different than that. If you look at the data sheet, it tells you that they start around 2,500, so the peak should come all the way down to sort of here somewhere, and they finish around 3,300, so it should end there. So a carboxylic acid peak would look something like that. Okay, so very different shaped peak altogether, and that's clearly not what you've got here. So an alcohol OH. This one, big strong peak in the middle. Again, if you look at the range of that peak, it's broadly consistent. You know, it's not going to be exactly right, but it's broadly consistent with what your data sheet says for a carbonyl peak, which is 1630 to 1820 wave numbers, and so you can say, right, there's a carbonyl group as well. So we know we've got both those groups, and we also know, of course, that we've only got one of each because there are only two oxygens in the structure. So therefore one of them must be an OH and one of them must be a carbonyl. So that bit of information is extremely useful when you get onto the NMR, and the important thing is not then to forget it and come up with structures which are not consistent with that. So this is what we've learned so far. We've got the molecular formula, we've learnt that from the infrared, and here's the NMR spectrum. So what I'm going to do first is to label the peaks in the NMR. So we're going to label them A, B, C, D, E. That makes it much neater when you're starting to try to explain what's what in the spectrum. So it's always a good plan to label them like that. We've also, of course, got the areas, which I hadn't marked on, but you had those in the picture as well. So lots of ways you could start, but where I would start was the fact that we know we've got one OH group, so there must be one peak corresponding to that hydrogen. It's got to have an area of 1, so it's got to be one or other of those two, because there's only one of it. And it can't be that one because it's split. Remember, OH peaks don't split. So we can straight away say, right, A is the OH peak. And the things that are important to say about that is that the area is 1 because there's one OH group, and it is a singlet. And it's worth commenting that OH don't split. You can talk about its chemical shift if you want, but remember, OH chemical shifts are not very meaningful, so there's probably not much point. Right, so then where do we go next? Well, I might be tempted to start with one or other of these peaks. When you see an area of 3, that's very, very likely to be a methyl group, so that's a good place to start because it's going to be you know, a sort of end of the chain in a way. So let's start with peak E and see what we can say about it. So we can say E is area 3, and we can say that that suggests a CH3 group. Obviously it doesn't absolutely prove that, because there could be 3 equivalent CHs, but it's very likely to be CH3, so let's run with that, see where it takes us. And the crucial thing is that it's a triplet. And the triplet tells us that there is an adjacent CH2. Okay, so you could say 2 hydrogens on the adjacent carbon, but somehow just writing that overcomplicates it. CH3 only has one bond, right? Because the 4 bonds of that carbon, 3 of them are to other hydrogens, so it only has one other bond, and therefore there must be a CH3 attached. So putting those together, we can say that we must have CH3, CH2. Okay, where those 3 hydrogens give you peak E. And the question I would then ask is, where's that peak? We know there must be a CH2 there, so there must be a peak corresponding to that CH2, and you can see straight away it's got to be C, because that's the only one with an area of 2. So that C is an area of 2, which is consistent with CH2. Okay, so we've made the connection between those 2 peaks and used it to identify a whole bit of structure. And that's what you should be trying to do. Not just documenting facts about each peak separately, but trying to link them together to build up bits of structure like that. And it doesn't stop there, because we can look some more at peak C and say, well, what else do we know about it? It's splitting. Well, that doesn't tell us anything we don't already know, really, because it just tells us it's consistent with the CH3, although it does tell us there are no more CHs on that side, otherwise it would be more complicated. But we can say it's a quartet consistent with the adjacent CH3, so that fits in, but it hasn't really advanced our understanding very much. But what doesn't help us is its chemical shift. So you can see it's between 2 and 3. If you look at your data sheet, there's 3 possibilities. There could be HCN, but there's no nitrogen. Could be HC aromatic, but there aren't enough carbons. So it's got to be an HCCO shift, which is 2 to 3 ppm. And so that carbonyl group must be next door, so we can add that on to what we must have, that we must have that in our structure. So we can get that whole chunk of structure just from looking at those 2 peaks, E and C. Okay, so now that's as far as we can go here, because of course the carbonyl group has no hydrogen, so there's no direct link to the next bit of the structure. So we look at what's left. So we've accounted for A, C and E, so we got this peak and this peak to look at. So let's look at D and say what we can say about that. Well, again, it's got an area of 3, so again we can say area is 3, which suggests that we have another methyl group, but this time the splitting is different, not a triplet but a doublet, so that tells us there's only 1 hydrogen next door, so we say that. So that means we just have an adjacent CH. And so we look for the peak that corresponds to that, and of course it's got to be B, because it's the only one left, but you can see it fits. It has an area of 1, because there's only 1 CH there, and it's a quartet split by the adjacent CH3. So that all fits together. So again, we can write that down. Say that we therefore know that we have CH3, CH, and I've drawn those 2 bonds there because obviously if there's just CH there, that carbon needs 4 bonds altogether, so we know there must be 2 other bonds to account for. And it's very useful to remember that, so that you think, right, what else have we got to stick on there? So again, we identify the specific hydrogens and say, right, that is coming from peak D, and this must give peak B. Okay, because, sorry, not the carbon, but the hydrogen there must give peak B, and we explain why it fits. Okay, area is 1, because there's 1 CH only in that position, and it's a quartet due to the adjacent CH3. Again, what that leaves is the chemical shift. So always think area, splitting, chemical shift. And the chemical shift here again is very interesting. If it's between 3 and 4, you look on your data sheet, and there could be halogens there, but we got no halogens, so the only thing that can be is an HCO shift. Okay, 3 to 4 ppm. Always quote the data sheet, just like you do with infrared, to back up that thing. So what that means is that again we can add to this and say, right, there must be an O there. Okay, so we've got CH3CHO, and we can say, well, what's that O attached to? Well, remember, going back to this, there are only 2 oxygens in the structure. It's obviously not the carbonyl one, because that doesn't have any hydrogens attached. So it's got to be this one. Okay, so we've got to have OH at that position. Okay, because otherwise there's no oxygens left for it to be anything else. So again, we can identify this bit of structure. Okay, so putting those two things together, we've therefore got CH3, CH2, CO attached to something, and we've got CH3, CH, OH attached to something. If you add up those two things, they account for all 5 carbons, they account for all 10 hydrogens, and they account for both oxygens. So in other words, those 2 bits add up to the whole structure, and all we've got to do is link them together. So obviously that bond is that bond, and that means the structure is CH3, CH2, CO, CH, OH, CH3. Final job is to go through and just check we've documented everything. I have actually missed a couple of things out. For example, I didn't talk about the chemical shifts of the CH3s, so you can just add that in and say, yeah, they've got HCR shifts. But actually what the examiners are going to be mainly interested in is, did you see the key to the connections between the peaks and therefore build up the structure in a logical way? So make sure that you've got the structure written clearly down. We've identified which peak corresponds to which as we go through, so you don't really need to show them again, but you could do that if you wanted to. But the main thing is that we've got a clear explanation of how the connections between the peaks are established using the splittings in the areas, and then how chemical shifts can be added into that mix to work out what else is attached, like carbonyl groups and oxygens and so on. So that's your answer.